All right, there's two more reactions of alkynes that I want to show you. These are analogous to reactions we've seen of alkenes, but there's going to be a little twist in the result. So you hopefully remember that we did see the reaction of an alkene with water. So if I took an alkene and reacted with H2O with an H plus catalyst, that it would yield, I'm going to flip this over just to be consistent, it would yield an alcohol. Turns out that with an alkene, we can do a similar reaction. In this case, we would make a product that we call an enol, ene coming from alkene and all coming from alcohol. But enols, it turns out, are not stable and generally will turn into an isomer themselves. So they'll undergo an isomerization. So I'm going to detail that. Let's just start with what we think the reaction mechanism would look like here. So our first step is going to be for PyCC to go attack the acid catalyst. That will give us an intermediate where we have a carbocation. I've mentioned this before. This is a vinyl carbocation, which is very unstable. I'll come back to that fact in a minute. But I'm going to take my vinyl cation, I'm going to attack it with the first nucleophile that's around. That is going to produce something that looks like my enol, except has an extra proton. So I would need to deprotonate. So that looks just like the reaction of water with an alkene with an acid catalyst. It turns out that under the usual circumstances where we would carry out this reaction, the acids that we use are just not strong enough, and this step is very, very slow, this first step, because the vinyl carbocation is so unstable. So we generally are going to add an additional catalyst to this reaction that will speed it up. The way it does so is more complicated, and I show it below, but it's not one that I'm going to require you to know. We're going to add a mercury 2 plus catalyst. We've seen mercury 2 plus before with oxymercuration reduction. So this reaction, the mercury is going to play a similar role. It's going to start by forming a mercurinium ion. Remember, mercurinium ion is less unstable than a carbocation. We then are going to attack with water, same way, deprotonate. And then there's these two steps to protonate the double bond and then remove the mercury 2 plus. These two steps definitely look strange. These are not required for you to know. But the idea is mercury 2 plus, because it goes through a less unstable intermediate, that speeds it up. So the bottom line I want you to know is that when we carry out this reaction, we will add in mercury 2 plus as a catalyst. To speed up that reaction. So that would make an enol, and everything would be fine and dandy if that were our final product. It turns out, though, that this difference in oxidation state between an alkyne and an alkene makes a difference. Now that I make this enol, it's not going to be a stable product. Enols will generally isomerize and create the corresponding ketone. We call this a tautomerization. So tautomerize means make an isomer by moving a proton. You might notice that an enol, and a ketone differ only in the placement of one hydrogen. So in the enol, I have a hydrogen on the oxygen, and I have two hydrogens on that carbon at the end. In the corresponding ketone, I've essentially moved one of those hydrogens. So how could I carry out a reaction where I am moving a hydrogen from one spot to another? Well, it's not exactly the same hydrogen. So I'm going to put moving in quotes here. They differ in the placement of one proton. So generally the way we'll do it is we'll add a proton on in one spot and then remove it from the other. So I have an alkene here, and I know that an alkene can go and grab a hydrogen by attacking with pi cc. So the first step here is going to be have the alkene go grab that proton. But that's going to leave behind a carbocation here. But what I want you to notice about that carbocation is it's resonance stabilized. There is a lone pair next door. And so what I've really created is a resonance stabilized carbocation. And now my last step would just be for a molecule of water, or I could use Sol here to come and deprotonate and make the corresponding ketone. All right, so this is an example of a tautomerization. We're just adding a proton in one spot, removing a proton from another spot, and the ultimate product of this reaction is a ketone. So in other words, we take our alkyne, we add water with mercury 2 plus and acid, and the result is to make a ketone. So if I have 1, 2, 3, 4 carbons here, I get 1, 2, 3, 4. I'd get a ketone on carbon 3. So it's a way to go from alkyne to a ketone. I ask, why wouldn't this reaction be synthetically useful for an asymmetric internal alkyne? Well, the issue is if I have a symmetric internal alkyne, or of the same R group on both sides, then I could imagine making two products. One where I put the ketone on the first carbon, and one where I put the ketone on the second carbon. The key is, as long as these two are the same, as long as the two R groups are the same, these molecules are identical. So for a symmetric alkyne, for a symmetric internal alkyne, we only make one product. For a terminal alkyne, we're always going to add the water to the oxygen to the more substituted carbon. So there we're always only going to make one product. But for an asymmetric internal alkyne, so if I had an alkyne where I had R, I'll call them R1 and R2, then I could make two different products. One where I add the ketone next to R1, and one where I add the ketone next to R2. And these are different products. So this gives me two different products. And generally, we like to avoid reactions that give us two different products because then we have to separate those products and it's harder to isolate the one that we want. So this is why it tells you you can turn a terminal alkyne or a symmetric internal alkyne into a ketone using this reaction. All right. So that's one reaction where we're adding water essentially to the alkyne instead of making an alcohol like it would have with an alkene. In this case, it makes a ketone. You might ask, what if I wanted to make an aldehyde instead? Do I have an anti-Markovnikov way to do this? The answer is yes. It's very similar to the way that we would make an anti-Markovnikov alcohol from an alkene. With an alkene, you hopefully remember that I could follow a sequence where I added BH3 and then H2O2 and base, and that would make an alcohol, adding the OH to the less substituted carbon. With an alkyne, we have to do something a little bit different. We have to add, instead of BH3, we'll add BH with a couple of bulky R groups on it. The point of these is to forces the BH part of the molecule to only react with one molecule. Which, when we're dealing with an alkyne, that piece is important. So we use something similar to BH3, but we're going to have two bulky R groups on it. Other than that, the reagents look the same. It's going to add the OH to the less substituted carbon. You do not need to know this mechanism. But know that it has the same result. It will make the enol. The thing about the enol is, just like the enol was in the previous case, that will get converted via tautomerization to the carbonyl form, in this case, the aldehyde form. The difference is, because we're in base, the order of steps is going to be opposite. So in an acid, when we did a tautomerization, we added a hydrogen first, and then we removed H plus from a different spot. When you're in base, there you have the reagent to remove H plus. So in base, you're going to remove H plus and then add H plus. This is a mechanism that you wouldn't see in most courses until much later. So I don't think you necessarily need to worry about it, but if you're interested, I'll draw it out at the very end. The one thing I want you to take away from this is that we can take a terminal alkyne so I'll just leave it generic and say R. And if we do this sequence, then we make an aldehyde. And just because you will probably see this if you look at various outside sources, um, one of the most common R2BH molecules that's used um, is called 9-BBN. 9-BBN is 9-borobicyclononane. It's this uh, bicyclic compound. Um, so if you ever see 9-BBN, that's what it's referring to. So the bottom line is we can take an alkyne and turn it into a ketone or turn it into an aldehyde, depending on our preference. Um, so that's the end of what you need to know. I will show the mechanism for this tautomerization now in case you're interested, but you can stop if you'd like. The way this would work is first, my base would deprotonate the OH group. That would give an intermediate that looks like this. Um, Note that this has an alternate resonance structure. Where the negative charge is on carbon. And we could then protonate at that carbon by removing hydrogen from water. So that would be the curved arrow mechanism for this tautomerization, in case you were interested. That's it. Those are the reactions of alkynes that I hope you know. Let me know what questions you have.